Okay, I will tell you about some of our recent experiments. I'm excited to also show you some new results from what we've been working on. And okay, this doesn't work either. Okay, this is a quantum simulation conference. This will be a talk that's about both error correction and quantum simulation, although more from an error correction lens. And as an experimental scientist, what I do find quite exciting is that the past decade has been quite remarkable in terms of the progress made across the field, where we now have such exquisite control over quantum systems that we can really start to use them for various things, such as trying to really make different types of quantum discoveries. There's already been lots of exciting talks today, and this dates back all the way to the optical lattice pioneers who are working on these quantum simulation experiments. There's also been really exciting work starting to take quantum bits and assemble them into more robust quantum bits using quantum error correction. And broadly, as we try to use quantum mechanics to do simulation and computation, the central challenge that we have to fight is that of decoherence. And the only known realistic route that we have in order to get to the scales required for certain large-scale algorithms that we find very interesting is the use of quantum error correction. And this is, in fact, so stringent that before this was invented, people thought that quantum computing would just be fundamentally impossible. So quantum error correction works in this quite funny way. You can't do the tricks that you do with classical error correction of just copying a bit because of this no cloning theorem. You also have this challenge that you can't check for an error without collapsing the state. But remarkably, quantum error correction is possible. What you do is you use entanglement in order to store information non-locally across many individual physical qubits. And by being delocalized, this qubit of information that you took and then hid across your many redundant physical qubits becomes hard to accidentally manipulate. And although we can't measure the individual qubits without collapsing the state, it turns out that by measuring products of qubits, you can still remove errors without revealing the underlying logical information. And I think that quantum error correction is actually, I think it's sometimes seen as more of a kind of engineering topic, but I think it's actually an extremely rich physics. I mean, it's also rich engineering, but it's an extremely rich physics topic. And I think that's really well captured by this famous argument between Peter Shor and Rolf Landauer, where there's this whole field that we don't talk about often of analog classical computation, which is actually extremely powerful. But Rolf was pinpointing on Shor, saying that we know that analog computers don't work because you can't correct errors. And Shor's response was that although the computation here is analog with quantum mechanics, the errors are digital. And it really kind of goes down to the core physics of quantum mechanics of this wave-particle duality. And I think it's actually quite foundational and quite amazing. And so I think a big message from the talk I will give you today is that quantum error correction, in my view, is an extremely exciting scientific frontier. And just like all other experiments, we do experiments, we learn things, and we do new experiments, and have a lot of fun doing that. Is there a mic making a weird sound, or is it only to me? Okay, fantastic. Okay. So a classic example of of quantum error correction is that of the toric code, where you have your error-free state of this logical qubit given by the state where all of these x and z products, these loops, are simultaneously equal to +1. And if you have an error on a specific physical qubit, it'll cause two of these checks to light up that you can measure without revealing the underlying state. And as we increase the lattice size, or our code distance d, we get more opportunities for errors, but we also get more checks. And this leads to a threshold behavior such that if we have, in principle, a sufficiently low error in the system, which is actually quite favorable, it's only on the scale of %, then we can actually start to have a realistic route to extremely small errors just by increasing the size of the code and exponentially suppressing the errors. And this is quite exciting, and it was really this theoretical breakthrough of quantum error correction that allowed this field of quantum computing to take off, because it started to seem that, oh, actually you can correct errors in these kind of analog type systems. And it is understood that eventually, we're learning so much doing algorithms with physical qubits, but in certain contexts, we will actually eventually have to start doing algorithms with logical qubits. And that's what we're going to study in today's talk. That being said, quantum error correction is extremely challenging. The optimistic estimates we often have in mind, as was discussed previously, is that you need millions of physical qubits, logical errors on the scale of 10 to the minus 10. And that's greatly further compounded by the way that we've built our modern quantum devices, which are often controlling qubit by qubit. And that's quite in contrast to our classical devices that work in a very different way, and you have 1,000 wires to control billions of bits by using much more efficient classical control. And so two of the really big outstanding challenges for quantum error correction so far have been this wire problem, and this has posed a significant challenge to large-scale control. Another significant challenge is that we take this logical qubit and then we hide it by spreading it across many physical qubits, but now it becomes hard to accidentally manipulate, it also becomes hard to intentionally manipulate. And so far, this has limited, the kind of studies in the field to, 1 or 2 logical qubits and operations. So in today's talk, I'll tell you about recent experiments we've been doing, including some new results, trying to advance this direction. And we're using these so-called reconfigurable atom arrays, heavily inspired by, a tremendous amount of work in the neutral atom tweezer community, also just the ultra-cold atom community. And the 2 really, really unique opportunities that you get in the system that I'll tell you about is non-local connectivity, which it turns out for error correction is extremely powerful, and also parallel and efficient classical control, which from an experimental perspective I cannot possibly stress enough is the key thing that enables these experiments. So, okay, so here is an outline of the talk. So first I'll tell you about some of the key components of our error-corrected quantum processing. Then in a little bit more of a quantum simulation flavor, I'll tell you about experiments we did studying quantum scrambling with error-corrected qubits and the interesting nuances and challenges of doing quantum simulation experiments with error correction. I'll tell you then about some new insights that we have after doing our experiments into the theory of fault tolerance and how we understand now things that are required for doing large-scale processing. And then I'll tell you about some of our new experimental tools for error-corrected science. Okay, so efficient classical control is the central message of the talk, at least on an experimental level. We use these neutral atoms trapped in tweezers, and then we entangle atoms through these so-called Rydberg states, which are these high-lying orbital states of the atom. The electron starts to orbit at hundreds of nanometers. And what's so special about these states is that they really strongly interact. And what happens is if you put 2 atoms next to each other and you simultaneously try to excite them to the Rydberg state, they will both compete to see who gets to go, but due to a really large energy penalty, they can't simultaneously go to the Rydberg state. That's this Rydberg blockade phenomenon, and this generates entanglement. So we've used this to study analog-type Hamiltonian evolution in a variety of different contexts. And this looks like, you assemble the atoms into some grid, you turn on some global excitation laser, and then you study the resulting Hamiltonian dynamics that come out. Once we want to do error correction and correct errors in the system, it starts to become really important to do things in a digital fashion. And digital systems are more nuanced. There are, all these fundamental building blocks that are composed. And although there are more degrees of freedom, we still really want to be able to have efficient classical control. And back in 2022, here what we were studying is this ability to, again, move atoms around in the middle of our computation. And we made here this Tor code on a torus. And here you can see in this movie exactly how we program quantum circuits. We have 16 data qubits here. They're fixed in our so-called SLM tweezers. It's one set of tweezers that we use that allows us to put atoms in arbitrary positions. And then we move these atoms around in so-called AOD tweezers, which are tweezers that allow us to move the atoms quickly across the system. And what we're doing here is just moving these atoms across the system. When we put 2 atoms next to each other, we pulse this global excitation laser and they entangle. And then we can do efficient control over these many physical qubits corresponding here to 2 logical qubits, just with order of 1 classical controls in the system. And when we were doing these experiments, it started to become obvious that this was a really, quite well suited to doing quantum error correction, because now, imagine that you're trying to do quantum computation not on physical qubits, but on logical qubits. We should start rethinking the problem in certain ways. We have the typical mantra that, to have our quantum computer, we need to have, an entangling gate and single qubit, arbitrary control. But once we have, logical qubits, it's a different question, because now we want to have single logical qubit control. And for example, if we want to do something like a single qubit gate on our surface code logical qubit, what it turns out we don't have to do is go and do something unique to each individual physical qubit of the block. We just essentially take this one effectively big atom and take one big beam and illuminate this big atom in a single parallel step in order to do a single qubit gate on this logical qubit in a fashion that we call transversal. But importantly, we can also do this for 2 qubit gates. If we want to entangle 2 logical qubits, all we have to do is pick up these 2 grids, interlace them with each other, pulse our 1 global pulse of our Rydberg entangling laser, and in this single parallel step, we entangle these 2 logical degrees of freedom. And if you look back at the history of fault tolerance when it was invented by Shor in '96, when we were first thinking about logical operations, this transversal nature is exactly the way that people were thinking about doing things. He has this comment in his paper that it's easily accomplished by doing these bitwise operations. Of course, he didn't mean easily from an experimental perspective, but indeed that is also the case here. And there's many benefits of this approach. This will be the key trick that's used in the experiments that I'll show you in today's talk. One really central benefit is that it's inherently fault tolerant. What this fault tolerance means here is that errors can't spread within the code block, and it prevents a single physical error from growing and corrupting your logical information. Another really important aspect is now in algorithms, we can start to do long-range and direct connections between logical qubits. And finally, it's really, from an experimental perspective, I cannot emphasize it enough, it's this question of efficient control, which is now, it's almost like we were doing a quantum circuit or a quantum simulation with our atoms, our physical atoms, but now we just do it with our big atoms, and then we can study the resulting quantum dynamics there. error-corrected systems. And using these techniques, we've studied here our first generation experiments studying logical processing. We have also these multiple zones that further allow us to abstract the control, similarly like in classical systems. So just to overview some of the programmable circuits that we did with these logical qubits, one of the first things you would always do is make a GHZ state. Here we made a GHZ state by making 10 so-called color codes. They're very similar to the surface code. And then you see how we're moving them around the system. And that single step, we did a transversal C0 between half the atoms. Then we pick up 2 of these logical qubits, start to slide them around, and in this way are doing a programmable Clifford circuit. We also did here mid-circuit error correction and feed forward in order to generate long-range entanglement between logical qubits, where we entangle these 2 degrees of freedom, and then we move a logical qubit all the way to the readout zone, measure it, and then conditioned on its state, do things to the other logical qubits, and start to explore these basic building blocks of error-corrected processing, as well as really, really heavily leveraging all these insights from classical processors, where you want to use zones, for example, to make your control more efficient, and then here by serializing, we can make as many as 40 of these distance 3 color codes. So those were some of the different programmable operations that we studied. One of the other things that you would do, when you have your new type of quantum system is make a Bell state and see how well you can make a Bell state. And here in particular, we're going to study how well we can make a Bell state between 2 logical qubits as we increase their code distance. And again, as mentioned earlier, one of the things that's really important in error correction is that we can actually improve our operations as we increase the system size. So here, the way we do this is we make 2 surface codes. These are these 2 distance 3 codes, as pictured here. We measure the stabilizers in a single step using these ancillas. Then we move the ancillas away and do our transversal C0. And we study here how well we can increase operations, the performance of operations as we increase the size of the code. And we're studying here a Bell state. So we, just like you would do with physical qubits, we look in the XX and ZZ basis. And this tells us, these are the Bell state stabilizers. It tells us about the fidelity of the system. And what we see is that as we increase the size of the code, we in fact improve how well we can entangle these 2 logical degrees of freedom, probed here by looking at these 2 Bell state stabilizers. One of the things that's really, really important to doing this experiment is the way that we do this so-called decoding. Decoding is, what I mean when I say decoding is we look at all of the stabilizers that are violated in the system and try to infer what error happened and then undo that error on our logical qubits. Here, once we start to do transversal operations, it's a pretty simple observation. Errors start to be very, very highly correlated between logical qubits, and you should really decode them jointly or in a correlated fashion. And this has continued to pan out to be an extremely powerful technique. And I'll tell you about at the end of the talk that, so here what we use this is to entangle 2 logical qubits with just doing a single round of stabilizer measurement. Typically, you think that you have to actually do so-called D rounds of stabilizer measurement in order to repeat your measurements over and over again and improve how well you can remove errors from the system. It turns out actually in this case that we now understand you never have to do this, and even for universal computation. So I'll tell you about this at the end of the talk. Let me check my time. Okay. So so there we were studying how well we can entangle these 2 logical degrees of freedom, as well as various programmable circuits. This is more of a quantum simulation audience, so I want to take a little bit more time on a more quantum simulation topic. And here, error correction codes, have various benefits, but they also have various constraints. They're extremely, extremely different than physical qubits. And one of the things that we really want to study is, are there particular algorithms that we can realize in a really efficient way with particular error correcting codes? And here, one of the things I've swept under the rug is something very, very intrinsic to this fact that error correction allows, that we can do error correction, is that our operations have to be digital. And we have to have a discrete gate set. And so for example, we have something like a Hadamard gate, an S gate, a C0 gate. These, for example, Clifford gates on the surface code or color code. And there's various challenges here, right? Because now it constrains what you can do. If you only have these Clifford gates, you actually can't do any classically complex simulation. So that is already kind of a letdown. But it's you can start to see that it's actually just so different than all of this intuition that we've built working with physical qubits essentially since the 40s with NMR. Because here with these logical qubits, continuous rotations are actually very hard. It's very hard to do a single qubit operation, but actually entangling is very easy. Almost all of these error correcting codes have an entangling operation, like I showed you in the previous slide. So it's actually a very, very different space, and it really starts to change the types of ways we think about quantum simulation. Take a quick pause. Okay, so with that being said, the idea that we had here is to, in fact, use a discrete gate set for quantum simulation. Michael, one of the organizers of this conference, was an extremely amazing collaborator during this process. You should also go and ask him questions. So it's hard to do arbitrary things, but not all interesting quantum simulations require to do arbitrary things. We also heard exciting talks earlier in this conference about doing quantum simulation with discrete gates. So here we studied these so-called 832 codes. I won't go into detail, but what these allow us to do is a non-Clifford gate, like a CCZ, and this generates complex entanglement, which is hard to simulate, and it generates so-called magic in the system, this non-Clifford character. And this codes have these constrained gates. They're allowed us to, there's 3 logical qubits and 1 cube, and then we can do a CCZ gate on the qubits within a cube, and we can do C0 gates between the cubes. And here we entangled everything on a hypercube, partially because it's really fun to say hypercube, and also because it generates fast information scrambling and rapid entanglement growth. It's actually very closely linked to black holes that scramble things in log time. And we study this here with our various logical qubits and doing hundreds of logical operations. And then we do a sampling experiment very similar to what was studied in the previous talk. And we study our sampling score as we increase the size of the system. No type of quantum supremacy claim or quantum advantage claim is being studied here. But we're studying, as we're doing these complex circuits, and we increase the size of the system, what we see is that we can actually do much, much better. Here, these 832 codes are actually an error detecting code, so we have to do post-selection for this experiment in particular, not in what I showed you earlier. But we can actually do it with post-selection. We can get a much better quality of samples with our error correcting codes than we can with our physical qubits. And it's an interesting trade-off. We heard in the previous talk about phase transitions in sampling. You could start to study these types of things because you have now a new knob, which is maybe you can pay more time, but you can improve the quality of your samples. And when you really stare at these samples, I think they're quite remarkable. And it starts to elucidate just how different these logical qubits are to our typical physical qubits. Where here we're studying 12 logical qubits that we entangled with the scrambling non-Clifford circuit. And here we're plotting these 2 to the 12 different outcomes. And everywhere across this theoretical distribution, you see a little experimental peak that follows. And if you zoom into the distribution further and further, if you track this red arrow, these small, tiny features here become these 2 big features in the bottom plot. And you can see even down to the noise floor, there you can reproduce the wiggles in the distribution with these error-correcting qubits. And this is not the type of thing that we see when we do physical qubit experiments. You have some coherent errors. The distribution is not quite what you expect. Maybe the fidelity is good, but there's some asymmetry. And it's a very, very different type of system where now you have this complex many-body state, and you can pick a very specific state in Hilbert space, and you can targetedly create this in a digital and precise fashion, create this many-body entanglement. And coming back to this famous argument between Shor and Landauer, I think you can really start to see why these are such interesting systems. And we, in fact, have started to quantify the fact here that what we see in this data is almost exclusively incoherent errors. When we do things with physical qubits, we have both incoherent and coherent errors. But here with logical qubits, coherent errors are very suppressed. So again, it's a very, very different type of system. And you can start to study really different things. And it really starts to change the way that we think about quantum simulation. So here's a movie of what exactly the scrambling circuit does. We make a 4-dimensional hypercube of logical qubits. And each logical qubit is a cube. So it's a 7-dimensional cube of physical qubits. And this movie shows how exactly we do this. I'm going to take a quick sip of water. We ran out of space there, so we moved our logical qubits and put them in the storage zone, picked up new qubits, did all these entangling operations all over again while our qubits in the storage zone are preserving coherence. And if there's one thing to take away from how we're doing this circuit, is that if you want to do this error-corrected circuit with all these logical qubits, it really, really does not make sense to have an individual 2-qubit gate control for each individual physical qubit. You should really have global 2-qubit gate controls for controlling all the logical qubits in parallel. That's really, I think, the central experimental takeaway. So as this is a quantum simulation conference, we're studying things like sampling and creating these complex states with quantum scrambling. But we like to probe, as physicists, we like to probe these systems in our various fun ways. So for example, we can do these 2-copy measurements where we take 2 copies of a scrambled state and then interfere them by doing a Bell basis measurement. And all of this is something that's quite advanced in our physical qubit quantum simulations. With logical qubits, it's pretty direct, because all you need to do is a transversal C0 and readout. And you can learn lots of things with these 2-copy type measurements. You can, for example, extract this entanglement entropy. And here what we see from our scrambling circuit is we generate this very, very complex entangled state, again, similar to black holes. And then as the system goes through this halfway point, it starts to realize that it's inside of a quantum simulator, and the entanglement starts to go down, and the system starts to approach the entanglement entropy for a pure state. Again, and we can see these really clean features now by using these error-corrected systems. And I think it starts to show that from a quantum simulation perspective and exploring interesting physics, these can already be quite interesting tools. And you can measure a lot of other things with two-copy methods. Here, for example, we measured the magic, which is the kind of amount of non-Cliffordness that we introduced into the state by doing this two-copy measurement. Excuse me. And we see that we can reproduce, that we indeed get the magic that we expect, and we can extract this from the system. Also, with these two-copy methods, one of the things that's been an exciting topic recently is people have been studying how to extract, a lot of information using these techniques. And it turns out if you do a two-copy measurement, you can extract all 4 to the n polystrings simultaneously, which is amazing. But unfortunately, you can only extract their absolute values, so it's not tomography. But still, it's an extremely powerful tool. And here, for example, what we see is we do this two-copy method, and we measure all of these polystrings. Here, due to structure in the circuit, there's only 5 unique poly values, and we extract here their expectation value, and we compare it, and as well as the purity that we measure in the system. And the purity should be 1, and the expectation values should be a little bit higher, but there is still some noise on our error-correcting qubits. But these objects are quite intricate, and they actually have these internal degrees of freedom of the stabilizers that tell us on each shot how likely we think we succeeded on this shot. And then we can actually do this what we call a sliding scale error detection, where we maybe accept more and more of our samples and our purity goes down, so do our expectation values, but in a correlated way, and then we can do a kind of zero noise extrapolation, totally integrated with this one data set. And combining these encoded qubits with two-copy measurements really starts to offer interesting possibilities in quantum simulation. Let me check the time. Okay. So that are some of the things that we studied. Starting to study quantum processing and quantum simulation with error-correcting qubits. To summarize some of our key findings, I think the one that I've emphasized significantly, but I'll say one more time, is that it's really what has enabled these experiments is parallel control over logical qubit blocks. This is an experiment. It's a typical atomic physics experiment built and operated by PhD students and postdocs in a basement. And when we're doing these circuits, the reason that we're able to handle the complexity is we're not programming a complex 70 physical qubit circuit. We're programming a simple 10 logical qubit circuit. And here, when we make this GHG state, for example, you see the types of diagrams that we draw for ourselves in the lab, where we have these 10 lines corresponding to these 10 logical qubits, and we program these transversal CZs, these transversal pi over 2s, just thinking about everything on the logical level. And that's what really enabled these experiments. In terms of some of our theoretical lessons, one of the things that was really important is that we learned that it's very important in these quantum error-correcting circuits to not think of logical qubits independently, but to consider the algorithm as a whole. We also developed some of these techniques of fault-tolerant compiling, where we take a specific algorithm and then try to tailor our error-correcting codes to it. We can start to see some of these features, such as the errors are digitized in the system, and we're really transitioning our theoretical efforts to focusing algorithms to error correction and focusing our error correction to algorithms. And it's quite nuanced, and it's not direct, just a direct extrapolation of what we do with physical qubits. So that's some of the things that we studied in last year. Now one of our central goals is to improve the performance and scope of these error-corrected algorithms, and I'll show you some kind of things in that direction. Yeah, okay, let me take a quick pause. I'm talking too fast and dehydrating myself, I apologize. Okay, let me slow down a bit. So, in addition to studying this error correction, we have diverse interests in our lab, and we are studying a variety of different things. So, one of them is that we're starting to try to use the system to do digital quantum simulation, very heavily inspired by superconducting and ion communities. And here, one of the simplest things that you would start with is doing something like trotterized evolution of a 1D Ising chain. And here what we do is we move atoms into pairs, pulse a global tunable C phase gate in order to do tunable C phase angles, but still using global parallel control. And then do this 1D Ising trotter evolution, study things like quenching to the critical point and so on. And can start to use this to understand the subtleties of doing digital simulation. Of course, now that you have things digitally, you can start to do much more programmable things, like, for example, studying new routes to non-abelian topological order, which is a really exciting recent topic. But, for example, on a cylinder because of the periodic boundary conditions in the system, and again, can realize this through, motion-based approaches. We also have been studying various other approaches to quantum simulation. So here, there's the two experts. There's Ryan, who's our, the theory expert, and Sophie is here somewhere, and okay, there's Sophie. So, okay, you can ask Sophie questions. So studying different types of analog evolution with our new tools that, of increased control, also studying things like, more advanced techniques for doing Hamiltonian engineering in this many-body system. And unfortunately, I can't go into this in detail. Of course, you should go ask Sophie some questions. But the thing that's so, interesting about hopping back and forth between these different modalities is, for example, when we do digital simulation, the world is our oyster, and we can study everything that we want. We can, do many different types of programmable gates, but errors have been really challenging, to be completely frank. And, that's something that's really interesting, because now we do it and we're like, wow, it sure would be nice if there was a way to remove errors. So it's actually, I think, been really stimulating to study the kind of differences here and, contrast error mitigation to error correction. And I think we've been learning a lot of lessons by comparing these various different approaches, although I can't kind of go into detail right now. So, okay, I'll take a quick sip of water. So these are some of our new experimental efforts. I also want to highlight some recent theoretical insights that we've gained. So one of the experiments that we did in our work was entangling these two logical qubits and doing just a single round of stabilizer measurement. And this contrasts with a lot of the kind of historical viewpoint in the field, where it's always been understood that to do logic operations on the surface code, you have to repeat your stabilizer measurements many times. You have to repeat it d times, where d is the code distance or the size of the code. And here in this experiment, what we did is transversal gates, which is also quite different than the typical approach, and only doing one stabilizer measurement per gate. And this generated a lot of discussion and debate. And I want to highlight now why exactly one would believe that this should work correctly, and also now highlight some of our new insights as to why indeed it does. And so here, I think a physics inspiration is very useful, where what I described earlier is these logical qubits. We take them and we hide them across many individual physical qubits. And now, if we want to entangle them with a transversal gate, what we do is we take these two delocalized wave functions and directly interact them through doing logic gates mediated directly through the data qubits. This is quite in contrast to a more conventional or 2D approach using a technique such as, for example, braiding or lattice surgery. In this approach, where you have atoms, qubits on a lattice, you realize logic gates not through transversal operations, but through ancilla stabilizer measurements. And you measure the stabilizers in order to, for example, entangle these 2 degrees of freedom across a boundary. And it's now extremely important to get these stabilizer measurements right. Because if you get it wrong, then you're going to do the wrong logic gate on the logical qubits. And so what you have to do is repeat it d times for certainty and fault tolerance. And the physics of this is that this delocalized info needs to travel through the boundary. It's very different here with transversal gates, where you do just direct entangling operations between physical qubits. And you still have to do stabilizer measurements, but they have a very, very different purpose. All they do is remove error. They just remove entropy from the system. And measurement errors are quite benign. If you have errors in this, if you have errors in your measurement, it'll just change how well you can remove errors from the system. And if you generate some degree of local entropy, you only need order of 1 stabilizer measurement in order to remove this local entropy. And you can do universal logic in this way with transversal operations. So the hypothesis here is that, in fact, by doing correct decoding in this system, we can use our transversal gates to do universal computation with just order of 1 stabilizer measurements per operation. And to go into some more detail of why exactly this works, so here in the context of this Bell state, and studying this again, this correlated decoding, when we prepare our ancilla with just doing a single, prepare our logical qubit with just doing a single round of stabilizer measurement, we get, in principle, can have errors in the middle of the system where we didn't successfully do our stabilizer measurement. And these errors will propagate to the other code and actually be, in fact, detected in the correlations between the 2 logical qubits. And when we initialize these 2 logical qubit blocks of this Bell state, then when we initialize the plus, we get X-type errors. And when we initialize the Z, we get the 0, we get Z-type errors. And now when we look at our XX and ZZ basis stabilizers, when you're looking in either of the 2 bases, you get the correlated errors that are important to you. You can clearly see these correlations between these 2 blocks, and you can undo this measurement error. And you might say, okay, well, you're cheating because you're only looking in the basis that's relevant to you. You're only looking in this XX and ZZ basis. What happens if you look in this XZ basis or ZX basis? Now you're not going to have all this information. You're only going to get one of the two pairs of this correlation. But importantly, if you make a Bell state and you measure an XZ, you're going to get 0 expectation value. It's not a stabilizer of the state. And it's just something that's 50-50 random, and it's not useful for you in terms of understanding what's going on. And the underlying core reason for this is that the initialization errors from doing just a single round of stabilizer measurement propagate in the exact same way as the logical operator. So we've studied this in, since our experiment in quite deep detail. So we do indeed see that for doing deep circuits, the exact same procedure works, where if we do just a single round of stabilizer measurement per logic operation, we can, in fact, remove entropy at a, constant rate. And as we increase the size of our code, we still maintain our, error correcting thresholds. And we see that we can get around with, get away with doing one stabilizer measurement roughly every 4 transversal gates. And this, for a deep Clifford circuit, allows us to just remove errors at the rate that we create them. And measurement errors, again, are benign because they just, propagate deterministically through the system. We've also studied this now in the context of universal computation. The key trick here is that universal computation is yet again just another Clifford circuit, but on poly inputs and magic state inputs. I don't have time to explain in extreme detail here. You can ask me more questions after. But for the exact same reason that the Bell state works, we also could do universal computation using these techniques. And the reason for this is you have this Clifford circuit on these poly inputs and T inputs, and measurements that you do that are commuting with a poly are insensitive to these initialization errors. Measurements that you do that are anti-commuting, like this XZ measurement, are sensitive to these initialization errors, but are also intrinsically 50-50 random, so they don't matter anyway. And then also the way you create this magic state is yet again just another Clifford circuit. On magic state input. So it turns out that the whole procedure works for universal computation. And in fact, what we see here is that we can reduce the number of stabilizer measurements we need to do by a factor of roughly 4D. We typically assume a D of roughly 30 for large-scale computation. And this now speeds things up by a factor of roughly 100 by doing these transversal operations. OK, fantastic. I'm on time. So these are some of our new theoretical insights. We also are developing new techniques in order to do measurement in different ways. So in conventional readout with these atomic systems, we typically have this issue where if we have these 2 qubit states, 0 and 1, and we try to image them, then what happens is that imaging actually mixes the qubit states together. And so in order to do high-fidelity imaging, what we do is we take one of the 2 qubit states, and then we eject it from the tweezer. And then now qubit state 1 gets ejected from the tweezer, and then we just image whether the atom is there or not through the spin-to-loss conversion. However, this greatly bottlenecks our cycle times. It also limits the error correction depth that we can achieve. And so it's quite powerful to study ways to do lossless and state-resolved readout. And for multiple reasons. One is that it's non-destructive. So now you can improve your cycle rate tremendously and extend how many measurements you can do with a fixed number of atoms. Also, direct observation of loss is a kind of erasure, and it improves your error correction thresholds. So here what we do is instead of converting spin to loss, we convert spin to position, really, really heavily inspired by the technique of Dave Weiss's group from this beautiful paper from 2019, where now we just take a qubit state and then we convert it into one of 2 positions. So the way that we do this here is that we have our atoms of our 2 different qubit states overlapped inside of a tweezer. We turn on a 1D lattice that we added into our system, which is circularly polarized. And what this allows us to do is trap just one of our 2 qubit states. So we turn on a lattice, we move our tweezer, and then now we just image the atom position normally. And now we're doing Rabi oscillations that we're measuring through the position of the atom. So this is what our new fun movies look like, where we're imaging the atoms in either the left position or the right position, but not there or missing. And then you can see here in these Rabi oscillations that we can track the Rabi oscillation but not lose the atoms from the system. And now we can do things like, for example, 100 times repeated Rabi oscillations, where we initialize our atoms, do a Rabi oscillation, do the spin to position conversion, image, and then recombine. And here what we see, this is first attempts and preliminary data. So I wouldn't read into the numbers too closely. But what you see is that we're doing many repeated Rabi oscillations. The contrast starts to go down because we do lose atoms at some finite rate. Of course, if we post-select on the atoms being present in the previous image, then it recovers to the right amplitude. There's some slow drift across the system because we have to change the way we're doing our power locking now that we're doing second-long quantum circuits. And yeah, we can still, I expect this number will significantly improve, but we have here roughly 99.3% survival per cycle. And we can start to study 100+ hertz cycle rates. Here we took images of our atoms with a 1 kilohertz cycle rate, and we can start to explore a new regime with atom array experiments, getting to much higher cycle rates. Of course, that's one really exciting avenue. Another one is to really start, thank you, try to explore deep computation. And we developed here new techniques. This is too technical, but it turns out you can do this technique of polarization gradient cooling, even if you have a finite magnetic field. I don't think I can go into detail on this one, but that's a new technique that enables us to image the atoms in a better way. We're here, you don't want to post-select on the atoms being present, so since the Rabi oscillation measurement, we developed new techniques to keep our array continuously filled, and we can start to study, initial experiments doing, for example, basic reloading from atomic clouds, really inspired by experiments in this atom array 2 group in our lab. And these new tools can really start to enable, quantum circuits that in principle can have, millions of 2-qubit gates. Of course, now that means we really need to use error correction in order to get to the large attainable depths that are attainable in the system. And it's been a very exciting year for these neutral atom systems where people have made, a variety of progress in various different labs and approaches. And I think that all of these things being combined together, there is a pretty exciting prospect in the not so distant future to being able to use these medium scale error corrected systems in order to study a new scientific frontier and study error correction and study quantum simulation in new ways. And okay, just to end my talk, so I hope what I really highlighted here in today's talk is that quantum simulation with error correcting qubits is a tremendous amount of fun, but also it actually starts to highlight extreme differences and nuances. We've been working with physical qubits, like 2-level systems, in many different contexts since the 40s. And all of these we understand in essentially the same way because it's a 2-level system. But these logical qubits are not 2-level systems. They're many-body systems, and they behave in extremely different ways, where, for example, single qubit rotations are hard and entangling gates are easy. And I think it's this really just like a qubit that we've, it's a type of qubit that we've never worked with before, and there's, many, many more types of discoveries that we can continue to make here. And I think the experimentation in the next few years will really hopefully inform next generations of that. So I would like to thank the amazing experimental and theoretical collaborators that participated in this work. Thank you.
Thanks. Time for questions. Dima.
Thanks, Dolev. Very, very nice talk. I had a simple question. So this approach of treating a logical qubit as one atom, right, and moving it around, and then sort of operating on all the physical qubits simultaneously, would it be prone to correlated errors?
That is a very popular question. So to the best of our understanding, no. We have characterized correlated errors. Here's a really, really central thing, which is that if you have this logical qubit and then you have a small angle error on all of the logical qubits of the block, then, all the physical qubits of the block, excuse me, when you do stabilizer measurement remarkably projects those all into uncorrelated errors that are uncorrelated incoherent errors. And that's why it works. It's because it's an analog system, but the errors are digitized. And otherwise, it wouldn't work. Of course, if you had a phase jump on all of the system, because you hit the microwave oscillator with a hammer, then that would be an issue. Similarly, we have one laser that traps all the atoms. If you block it, then all the atoms are going to go away. So you need to not do those things, but we're not aware of any large-scale errors like that.
Manu? Thank you.
Actually, let me just ask, can you comment more on the difficulties for analog, for doing the time evolution? I mean, you were a bit short on that. Doing in a digitized way, using, the fantastic capabilities that you showed, and then trying to use time evolution, you said that was not so easy, actually.
Well, with like physical qubits, not logical qubits.
Yeah.
So it works, right? We are studying, and we're at the beginning, right? And we can now study many different models. The analog systems, they just kind of evolve, and then when you have dissipation or coherent errors, they just kind of change what you do often. With the digital systems, errors happen and then propagate. So I think it's nuanced to the differences. Still, I think there's some constant factor difference between them. It's not some exponential factor, but it is nuanced, and I think we're studying the differences there for sure.
So what about prospects then for doing like time evolution with your logical qubits?
Oh, so I would say we did time evolution with our logical qubits here. To do much deeper evolution, we need to get very good at removing errors from the system as we do it. But I think the prospects are bright. It's just lots of work to do. Yeah.
One last question.
Thank you for the really nice results. Can you give us an idea or just help us understand a little bit, how do you deal with the loss of atoms in quantum error correction as you would push to deeper and deeper cycles?
That's a great question. Yeah, so loss is this interesting error that really needs to be corrected, because once you lose all the atoms of a code, the information is gone. So definitely we have to replace atom loss. That being said, we have a whole host of different techniques, and actually our current understanding is loss is a more favorable error. So it's important to be able to handle it, but actually as long as you're clever with how exactly you leverage it, you can actually sometimes even use it to improve your threshold. These are techniques pioneered by, for example, Jeff Thompson and Shruti Puri. Understanding that loss can actually sometimes give you more information, right? So important, very important to address. Otherwise, all the atoms disappear, but also definitely not a fundamental roadblock.
All right, let's thank Dolev once again.